Okay, well, welcome to, good afternoon, everyone, and welcome to this first of our postgraduate tribology webinars. It's a new initiative from the IMechE Tribology group, where we will bring together postgraduate students, PhD students, MSc students from around the UK to present their research, their PhD research and MSc research in tribology. And the plan is that we'll have one of these webinars every month. Except in December, and would be from 12 to 1, probably on Fridays. And this is the very first of the new tribology webinars. So what I'll do now is just introduce our first speaker. So our first speaker today is Emily Priest from the University of Sheffield. And the title of Emily's talk is Modeling the Pressure Distribution of a Tilting Pad Journal Bearing as the Main Bearing in a Wind Turbine for use in wear test experiments. Emily is a second-year PhD student at the University of Sheffield in the Leonardo Tribology Centre. Her work is sponsored by the Offshore Renewable Energy Catapult, and her research focuses on the wear of pads in tilted pad journal bearings for use in the main bearing in offshore wind turbines. So I'll just introduce Emily and invite Emily to give the first presentation. And just to mention as well, if you have questions, because of the platform we have, you can't actually orally ask the question at the end of the presentation. So if you can text the questions into the Ask a Question tab, if you can find that tab and just type in your question very briefly, we'll be able to ask Emily after the presentation. We'll be able to put those questions to the presenter after the presentation. So thanks very much, everyone. I'll just hand over to Emily.
Hi, thank you for introducing me, Daniel. Like Daniel said, I'm a second-year PhD student at the University of Sheffield, sponsored by the Offshore Renewable Energy Catapult, and I'm researching the modelling and loading of tilting pad journal bearings in the main bearing of a wind turbine for use in material testing. So I'm first going to start off with a little bit of project background before I move further into my research. So just moving into the current bearing technology. So the main bearing sits on a wind turbine drivetrain between either the rotor and the gearbox, if the drivetrain has a gearbox, or the rotor and the generator. At the minute, the main technology used for this main bearing is rolling element bearings. So that could be spherical roller bearings or tapered or cylindrical roller bearings. And they just take all the load that's non-torque experienced at the rotor. So that will be load not caused by the turning, but caused by the wind loading of the rotor. There's been massive developments in wind turbine technology recently, a lot of investment, and the trend is to just keep on going bigger in terms of the power capacity. So you can see back in 2000 from that graph, we were kind of prototyping kind of like 3 megawatt wind turbine capacity, but now we're going up to 16-20 megawatts wind turbine capacity. And with an increase of power capacity, we get an increase in wind turbine size. So you can see from the right-hand figure there, we get an increase in rotor diameter and hub height as we increase in the power. And that leads to perhaps changing technology a bit. So the change in technology that I'm researching is the use of tilting pad journal bearings. And if you don't know what a tilting pad journal bearing is, here it is on the drivetrain. It's a classic journal bearing. So that is a shaft sitting kind of in a bush, and the actual bearing is segmented into pads, which then are pivoted. And as the shaft spins inside the bearing, the different pads will tilt, and a lubrication film will be built between the shaft and the pad. And this is just a little animation of what happens, and you can see that the actual bearing can actually be assembled on the shaft, which is pretty useful, as I'll go on to explain now. So yeah, what is the advantage of this technology over using the classic rolling element bearings? So there isn't a 4-meter diameter limit for the transportation with trucks. So as we go towards 20 megawatt wind turbines, we're looking at more of like a 5-6 meter diameter bearing we're needing. And if we use our rolling element bearings, we can't break those up. We have to transport them fully assembled, and they can't actually fit onto trucks. And that becomes a massive issue when transporting. As you saw on the earlier animation, our pads can also be replaced in situ, which helps reduce downtime and maintenance costs. And it also means smaller vessels can be used because you can transport parts separately. And yeah, like I said, downtime reduced. So for use in these bigger wind turbines with these bigger bearing diameters, it makes a lot of economic sense to move towards tilting pad journal bearing technology. But there's a lot of issues facing this industry, this part of research, because there hasn't been a lot of research into this. And I believe there is only one wind turbine in the world using this technology currently. And traditionally, these types of bearings are used in very high speed applications, whereas wind turbines operate at very low speeds. And we also have a high number of start-stops. And these start-stops happen due to the cut-out and cut-in of wind speed. So when the wind turbine's operating at too low speeds, the wind turbine won't be turning and it will shut down. Or if it goes too high, it threatens the mechanics of the wind turbine, and therefore the wind turbine also shuts down. And this is all tribologically important, as I'm sure a lot of you already understand, because as we decrease the speed of the rotation of the wind turbine, we move from hydrodynamic lubrication, if we were even there to start with, as like I said, wind turbines operating at these really low speeds, down through mixed and boundary lubrication, and we begin to get asperity contact, and this leads to adhesive wear, plastic flow, and potential catastrophic failure. So the solution for this is what I'm researching in my PhD. So it's using material coatings on the tilting pads in order to protect them. So traditionally, again, in tilting pad journal bearings, white babbitt is put onto the surface of the pad, which wears pretty easily. So I'm looking at material coatings such as PEEK in order to reduce the friction coefficient and reduce the wear experienced on the pad. But like I said, this is a new area. So there isn't literature on the pressure distribution on the pad and the wind turbine, or quantifying of or the impact of start-stops, or the conditions of the pads in the wind turbines, like the lubrication film thickness. So also that is the conditions experienced to tell us which lubrication regime it's in. So that, again, moving back to that boundary mix or hydrodynamic lubrication. So I'm studying the wind turbine behaviour and modelling the bearing loading to inform a test matrix for this material, for material coating testing. So filling in those blanks basically with my PhD. So moving on to the modelling I've been conducting. So I'm using this drivetrain arrangement. So here we've got 2 bearings, and this will be a journal pad bearing straight next to a thrust pad bearing, and then again further down the drivetrain again. I'm just focusing on the journal bearing rather than the thrust pad bearing in my research. And this can be modelled as a simply supported beam, where the 2 supports are the 2 main bearings, the journal main bearings. And we're assuming that these 2 main bearings are taking all the non-torque loads experienced at the rotor, and the gearbox does not take those. And we have simulated data from the rotor, which then can be translated to the forces experienced at the 2 main bearings. So like I said, we have our simulated data, and then we can input simulated data into that simple arrangement I just showed you in the earlier slide. And we get loading around the bearing. If you imagine the center of the bearing being at the origin of this axis, then we can see the load varies where it points around the bearing, like that. We can then input this into a definition made for where the different pads sit in the bearing, and we can study the load and frequency of loading experienced on each of the different pads. So here is just a selection of some of the results I've generated. So we have the pressure experienced on each pad there, just for different wind speeds of simulated data. So we're getting around 5 megapascals. We can also see the frequency of loading on each pad, and this is just across 600 seconds. So you can see that just tells us which pads we need to focus on and what loads we need to be testing them at, and how many revolutions we need to test them at. So moving to like a different side of the modelling, I've also been studying the Reynolds equation, and that's to tell me stuff like the film thickness. And as explained before, we need to know that to know what kind of lubrication regime we're working on for material testing. So I've just done some work deriving some of the equations, and I'm hoping to link this up with the work I've just explained previously in some future work. So moving on to the study of SCADA data. So SCADA data is just real life data collected at the wind turbine. So you get stuff like rotational speed, power, temperature, time, etc. in a spreadsheet, which you can then build algorithms to analyze. So that's what I've done. So you can see one of the things I've studied is the shutdown events over a year. So you can see there I've plotted shutdown events per day over the year, and I've also conducted this for stuff like when the wind turbine's idling. And then I've gone and related this to wind speed, because this is a 3 megawatt wind turbine, so I needed a way to say, does this apply to a 20 megawatt wind turbine? And the wind speed doesn't change between those, so I've shown that it correlates, and therefore I can use it for my 20 megawatt wind turbine also. And this will inform my test matrix. So moving on to my platform for material testing, I'm using the Phoenix Tribology tribometer, and this uses pneumatic loading, and the arms load onto a specimen, and I can measure torque for friction measurements at the front there also. Currently I've just been testing with peak, and you can see my arrangement that I have here. So I have my 2 peak specimens, which are conformal blocks, and they go around a steel disc, and then the steel disc then spins, and I can conduct the material wear test using this. And into this machine I can input the loading data that I've just shown, the start-stop data I've just shown, to try and test this peak material as if it were in a tilting pad journal bearing. This work's still very much ongoing, but I just thought I'd show you like a selection of some of the data I've collected. So you can see that I can see friction coefficient, temperature measurements, and I also have conductor measurements using a 3D microscope to give me an accurate image of what's happening with the wear on the specimens, and what the wear distribution looks like after testing. So then just leads me on to my last slide, which is what's next for my PhD. So I have a bit of time left because I'm just at the start of my second year of my PhD, so I have 2.5 years left. I'm currently conducting testing on the tribometer I just showed you with the parameters I found so far, so hopefully I'll get some results on that. soon. I'm also looking to select further materials to test. So I'm just testing with PEEK at the minute. I'm hoping to maybe test with possibly ceramics and hardides and anything else I really conclude on testing on. I want to further develop my model of the pressure distribution and the film thickness on pads to better inform my test matrix. And finally, I'm building a full tilting pad journal bearing test rig, and that journal bearing test rig will have tilting pads which will be lined with PEEK, and I'll also have some ultrasound sensors in there to measure film thickness, and that will just give me a very much fuller picture as well. But yeah, that's everything. Thank you for listening.
Thanks very much, Emily, for that very excellent presentation. So we have a couple of questions in the chat box, I think. There's a couple of questions from Jim Quinn. First one is, where do you take the axial load?
So because I'm not currently concerned with the thrust pad bearing, I'm not actually looking at the actual load. I'm assuming that's all taken by the thrust pad bearing, which I'm not studying currently. I'm just studying the journal pad bearing, so I'm just looking at the radial loads.
Okay, great. And the next question, also from Jim, is what brinelling problems do you have when the turbine is static?
Sorry, could you repeat that?
So it's what brinelling problems when the turbine is static. This is like the indentation of the race, damaging of the race from all these indentations.
Oh, I'm not too sure on that one. Sorry, I'm just studying the actual pads rather than the raceway.
Okay. Yes. Okay. Maybe that's more common in roller bearings, perhaps. And there's a question from Michael McPadden. How does temperature affect the situation? The temperatures that you generate in this situation.
So in terms of temperature, the temperature of the bearing will be at a temperature of 70 degrees probably. That's what we think, because we think the oil feed temperature will be 70 degrees, and that will obviously soften the material of the PEEK, etc. So probably make wear more easier. But as if for like how it affects things, I guess I'll find out because I'm trying to test at this 70-degree temperature. But yeah, that might be a question to ask me in a few years.
Yes, actually, Michael's question is more extensive when I expanded a bit.
Mm-hmm.
It's how does temperature affect performance of the pads of the different seasons? As well, you will consider how salt water content in the air affects performance. So have you looked at this aspect of salt water, for example?
Yeah, starting off with the temperature thing, although I think I just explained it, the temperature should be pretty constant at the 70 degrees. The salt water question is really interesting, and that's definitely something I would look into, potentially putting particles into my lubricant to see how that has an abrasive effect on the pads, for sure.
Great. There's a question from Kate Tomlinson here. Thank you for a really interesting talk. Are there any other industries that you are drawing inspiration for coatings?
Yeah, I think what I've been looking at the minute is it sounds a bit weird, but looking at hip replacements, because they actually operate at pretty like low sliding speeds like the wind turbines do. So I've been taking inspiration from there, seeing what coatings they use and trying to select my materials through that a bit.
Okay, and there's another question from Ketano Peng. Are you considering measuring contact stiffness and surface erosion in addition to friction?
In terms of surface erosion, do you mean, is that like linking back to the salt water?
I'm not sure what exactly is intended. I guess it could be a corrosion situation.
Yeah, I'm measuring I think in answer to that, like, yeah, I'm measuring the friction coefficient, but as I think I showed that slide that showed my 3D imaging with a 3D microscope, and through that I can see all the wear. So I have abrasive wear, I can see that really clearly, and all the different types of wear. So in your answer, yeah, I am studying the actual surface effects as well as the friction coefficient.
Great. One question I might ask, let's say, how are you planning to measure the pressure distribution that you get between the pads? How are you planning to actually make that measurement?
Yep, that's a good question. So linking back to the Reynolds equation that I showed, that includes a film thickness term. And hopefully when I've kind of completed my model, I can link film thickness to pressure. And then I'm going to be going on to testing. I already do quite a bit of testing with ultrasound to measure film thickness. But when I have my full scale test rig, I can measure that film thickness, and that will inform a pressure for me.
Excellent. So I'm not sure. There don't seem to be too many more questions at the moment. You can always ask a question which can be answered at the end of the next talk as well. So if you think of any more questions, you could also put them into the text box. So let's thank Emily again for an excellent talk and for being the first speaker in the Tribology webinar series. So thanks very much, Emily.
Yeah, thank you, Daniel.
So our next speaker, this is our second speaker. This is Dhanushka Amaradasa from the University of Central Lancashire. Dhanushka graduated from the University of Rahuna, Sri Lanka, with a BSc in physics in 2014. He started his research career in astronomy instrumentation in 2015 and completed his master's in the same field in 2021. Dhanushka is currently a first-year doctoral student at the Jost Institute for Tribology at the University of Central Lancashire, where his research interests include electronics and space tribology. And this is a quite interesting topic. The title is the Tribology in Space, which a lot of us haven't talked very much about, I guess. So it's an interesting topic indeed, tribology in space. So let me hand over to Dhanushka for the second of the two talks.
Hello, everyone. First of all, I would like to consider this as a privilege, making a talk at this first IMechE webinar series. So I would like to thank David for my colleague who actually suggested me this opportunity. My project title is a CubeSat platform for testing space lubricants. So I'll be mainly talking about tribology in space, or as we call it, space tribology. Okay, so let me give a brief introduction about myself. I think Daniel gave a good introduction. So my name is Dhanushka. You can call me Dan. To be honest, this is just a half of my name. I have a kind of a huge name. So previously, I have been working with astronomy instruments. To be specific, I was designing telescope tracking systems. So I started my PhD in January 2023. So I just started. I just finished my literature review and kind of working at the moment, working in the designing and prototyping. Okay, so what is space tribology and how it is different from terrestrial tribology? So whenever I imagine space tribology or tribology in space, this is how this picture created by Open ChatGPT, Dolly. So this is how I imagine. This is tribology without service and maintenance. So how many of you tribologists actually have the challenge of designing something with zero service and zero maintenance? I have that challenge as a space tribologist. So in space, since you don't have any chance to maintain service, so it's just driving millions and millions of miles without changing oil. So that's how I kind of picture space tribology. Okay, so if you want a textbook definition, so this is it. So tribology is generally wear, lubrication, and friction. So space tribology is mainly concerned on the space environment like microgravity, radiation, temperature, vacuum, and launch conditions. So in space tribology, we will be mainly planning mechanisms which can endure these environments. So space tribology aims to design reliable tribological systems that can withstand the harsh environment of space. So what are these challenges in space? Microgravity. So if you take a liquid in zero gravity, it will behave, it will make a complete sphere. So what will happen to the liquid lubricants if you use it in a zero gravity condition? And vacuum. So in a low pressure conditions, all the materials outgas. So this outgas process is kind of reduce the mass of the materials and maybe induce corrosion. And temperature variations in space, any spacecraft will actually undergo minus 50 degrees to 150 degrees temperature variation. So it's a massive variation, especially when it is ascending from the launch to the low Earth orbit. There's a huge temperature change happens within a very short time period. So it will induce a thermal shock in all the mechanisms. So we have to design systems which can withstand these conditions. And radiation. There are many types of radiation in space. So if you consider sun as a black body, so yeah, I have a background in astronomy. So, black body is an object which can emit all the spectrum of the radiation. So sun emits from radio waves to X-rays. So especially in low Earth orbit, this radiation can actually interfere with oxygen atoms and create a highly corrosive free radical called atomic oxygen. So this atomic oxygen is kind of corroding metals and especially the lubricants. And finally, launch restrictions. So after all, still we are using 50-year-old rocketry systems to launch these spacecrafts to space. So when we launch, it undergoes massive vibration. It's around 20 to 2000 megahertz. So imagine designing a tribological system which can measure and calibrate well your lubricants and the lubricants. But you still have to design the tribological mechanism in such a way that it can withstand this type of vibration. So it's a huge task designing these things. And loss of lubricants. So during storage, most of the times these space missions can get delayed. So these spacecraft might stay in a storage in NASA or ESA for maybe 2 years or 3 years. So we have to consider the shelf life of the lubricants and the mechanism when we are designing space mechanisms. So after all, weight of the payload. So just like terrestrial tribology, okay, I think it might be a bit offensive to use terrestrial tribology because tribology is all about terrestrial stuff. But yeah, so we don't have the privilege of designing sophisticated, very massive instrument in space tribology because weight matters and weight is equal to cost. So we have to design very economical systems as well. So moving on, what type of so when do spacecraft mechanisms function? So it starts even before launching, pre-flight, during storage, and before launching, we have to standardize everything and do standardization tests. So during that test, these mechanisms should function properly. And at launch, electrical and fluid disconnects from the main rocket. And during ascent, a spacecraft and sub-satellite separation should activate. And after achieving orbit, the doors, covers, and solar panels, and maybe in James Webb Space Telescope's case, this sun shield should launch. So throughout the mission, the solar panels should be tracking the sun or maybe energy source nearby. And there are a lot of mechanisms there which should be functioning throughout the mission, like active doors and shields. So this is the James Webb. So this is launched. This was launched in 2021, as I remember. I think it's 25th of December. Yeah. So this was delayed. I think around 2 years for the COVID and everything. This design actually relies on this sun shielding mechanism. As you see here, there's an aluminium foil type. Yeah, it looks like that, but it's not aluminium. So this sun shield should be deployed correctly. Otherwise, the James Webb telescopes cannot focus in a particular part of the space because of the radiation of the sun. So imagine launching this system and the sun shielding mechanism kind of refused to open. So the entire mission is going to kind of fail. Okay, so there are a lot of mechanisms in space. So let's see how fast do these mechanisms function. So we have, especially we have rolling and linear, both motions, but here I'm considering only rolling motion. So we have slow moving parts like solar array deployments, solar array driving mechanisms, as we call them, or and medium, like camera pointing mechanisms, antennas, and fast-moving mechanisms like reaction wheels, gyroscopes. So this video shows the solar array of the International Space Station. So this is a crucial thing to function. I think there was during last 10 years, there was a failure in the solar array driving mechanism of the space station. So there was a huge risk that the astronaut inside the ISS would lose power and life support system because of this failure. I think they managed to kind of reinstall this driving mechanism mid-air. It's kind of a daring mission with a very long spacewalk. So, but in space, it's not actually affordable to maintain or service because of the space environment. It's really, really difficult. Okay, so as tribologists, this is what we are looking for. How long do these mechanisms function? As you see, SADMS stands for Solar Array Driving Mechanisms. So they are the actually slowest moving part. So pointing mechanisms and these spinning scanners and wheels. So reaction wheels are the kind of main part of a space tribological system, which requires a very long lifetime or large revolutions. Okay, so what type of lubricants do we use in space? So it's again, there are specific space lubricants. So MOS2 is the kind of most famous. So I consider it as the most senior superstar of space lubricants, because this has been used for maybe last 20 years, for no more than that, and this is kind of a reliable lubricant currently used in space tribology. So it has low friction, high wear resistant, stable in vacuum, but it has a huge downside, that's degradation in humid conditions. Usually when the spacecraft is stored in a storage, because of the humidity in Earth's atmosphere, the lubricants start to degrade and oxidation. So the other commonly used, I think I should mention, it was used commonly, but now it's kind of not using because of the lead is kind of commonly used. It has a very good kind of property. It is self-replenishing, so it's kind of servicing itself, but it is toxic to human. So when we store and test this spacecraft in laboratories, it's kind of hazardous. So I think now no longer the lead is no longer in the list. Okay, so the PFP is kind of a new star, and it's kind of used frequently now. And the other mainly used lubricant is IMechE. So it is kind of low cost and low cost and high wear resistance, and it has a low friction coefficient. So these are some of the lubricants used in space. But to be accurate, rather than this, there are a lot of kind of new lubricants, and maybe not only single lubricants. They use compound. That means they use sandwich type of layered lubricants in space. So these are the basics, basic lubricants space mechanisms use. Okay, so this is the James Webb Space Telescope. Yeah, it has a filter wheel. Okay, since my background in astronomy, I will explain what a filter wheel for a telescope is. So this filter wheel is kind of rotating in front of the camera, so it can actually filter out different wavelengths. So it has to function throughout the mission, maybe 10 years, 15 years, 20 years. So here they have used MOS2 again, so black coating. Okay, so it's all, so in James Webb Space Telescope's case, it functioned well. It's functioning well. I hope so. It will be functioning well in future as well. Yeah. So, but it's not always the case. There are a lot of lubrication related failures. So space mission related projects are considered challenging and prone to high rate of failure. Yeah, it's a challenging task. And mechanical issues such as lubrication failure accounts for around 32% of spacecraft failures. And the majority of the tribological failures can be considered as single point of failures. So we call it SP of FF. So in terrestrial tribology, I think this type of single point failures are not a big deal because you can always service and maintain. But in space tribology, it's going to be different because if a SP of Fs happen, it's going to be the end of your mission because it's kind of sabotage the entire mission. So that's what happened in Galileo spacecraft, Galileo mission. I think it's in 1980s. They launched the Galileo spacecraft to kind of search and take pictures of Jupiter, and it reached the Jupiter orbit without a problem. But this umbrella-like main high-gain antenna, they have a lot of hooks and kind of pins. That one pin actually kind of stuck and didn't open well. So after going to the Jupiter, it actually could not effectively communicate with Earth. So we lost a lot of scientific data, but eventually they figured it out and actually tried to use the smaller antenna, but the bandwidth was really kind of low. So I always imagine this scenario as kind of going to a very nice place, maybe climbing a mountain, maybe in Lake District, and kind of taking a picture, and you cannot upload it into your Facebook profile or Instagram. So it's just like it's very similar to that, but we lost a lot of scientific data in Galileo mission. So Hubble Space Telescope had a similar problem after launching. The aperture door actually had a problem with lubricants and it didn't open well. And during Rosetta mission, anomalous torque behavior, actually this was very prominent kind of a failure during late 80s because nobody knew how these reaction wheels, the bearings in the reaction wheels perform. So there were a lot of failures, and some people speculated that this could be aliens disrupting our space endeavor. So, but no, there were no aliens involved. So the problem was actually with the metal bearings due to solar radiation whenever there's a coronal mass ejections. So these type of radiations could actually induce a huge magnetic field through the bearing, and it will induce arc pitting. So it will actually fail eventually, not fail completely, but it will increase the torque. This reaction wheels is the kind of eyes and ears of the spacecraft. It shows which direction it is oriented and which direction it should be going. So without the reaction wheels, the spacecraft is kind of a stationary object. Okay. Yeah, Kepler telescope had the same problem with the reaction wheels. Okay, so yeah, we have a lot of problems. So how do we make sure these space tribological mechanisms function well without a problem? So we have to do tests, right? Yeah, all the tribology the basic of tribology is test, and test. Yeah, we can do ground-based tests. Most of the tests are conducted in tribometers located inside vacuum chambers. So we have a pin on disk in a vacuum chamber. We have MTM in vacuum chamber. And most importantly, spiral orbit tribometer. It's kind of I think it was introduced in early 2000s, and actually it has been used a lot to analyze the lifetime of lubricants. So these type of ground-based tests are kind of crucial, but still there's a debate about space-based tests, because there are only few dedicated missions with uniquely designed tribometers. Why? The reason is space is kind of really expensive. That's why I use this meme. We don't do that here because it's expensive. Usually in NASA and ESA use heritage. What is heritage? Depending on the previous mission. So if the previous mission worked well, all the lubricants worked well, so we will use the same lubricants, same mechanism in the next mission. So it makes sense, because we cannot test new lubricants or new mechanisms in space. So what do you think? Do we kind of focus more on space-based tests, or should ground-based tests enough for kind of increase in reliability of these space tribology mechanisms? Okay. Yeah, there are already few. I think after 2000, during the last 2 decades, there are only, I think, 4 to 5 space-based tribological tests. This is one of the main tests conducted. So it's called IMechE 7. It launched 18 tribological experiments, but 8 tribometers were there. Okay, this is your well-known pin-on-disk mechanisms, but it is in space, so it has designed in such a way that all the materials will be space compatible. You can see kept on tapes. So that's kind of vacuum compatible tapes. Okay, so there are around 4, but I have selected only 2. These are the kind of main tribological tests done in space. Tribocosmos project. So they have started this project in 2010, but due to a lot of postponing, I think they have launched this mechanism into International Space Station. There's a research paper telling that it was launched, but after that I don't find any information or results of this tribological setup. So this content, according to their 2010 paper, this contains a journal bearing test and a pin-on-disk as well. What is inside, I don't know, because this is the only picture they have published, and there are only few information about this. So if you know anything about this test or these researchers, so you can please tell me. Okay. So this is my research problem. Cost of space-based research is really high, so we have to still do space-based test. To increase the understanding of the performance and lubricants in space, we have to design a low-cost way of testing these mechanisms. So this picture shows ESA astronaut actually repairing Hubble Space Telescopes. So this type of repair and services are not frequent. Okay, this is a very rare thing. Okay, so how do we justify space-based test? So this is a kind of a analogy. If you have referred Bharat Bhusan, the tribology handbook, you can see this type of a similar analogy illustration, which has done for a car engine. So when we start from a pin-on-disk, so I have done this. That's the same analogy to a spacecraft. So let me explain this. If you take a pin-on-disk test, and if you use the lubricant we use in the bearing in a pin-on-disk test, it will be a model test. And if we increase the degree of realism and reliability, so we can go for a simplified component test like 4-ball test. And we can actually test the whole component itself, like the bearing, and the system. The whole reaction wheel can be tested as well. And eventually we have to test the kind of entire mechanism in a spacecraft. So that's the challenge. We don't have it's not economical to kind of completely sending a huge spacecraft to space and test it. Okay, if you need more details on this, we have made a kind of a publication, so you can refer to that and cite that. Okay, cite it. Okay, so this is our kind of spacecraft. This is how we kind of reduce the cost. This is called a CubeSat. It is mainly used in scientific, commercial, and educational space missions. it's just a 10 by 10 cube, and it has a maximum weight of 1.3 kilograms. Okay, so our objective is to design, build, and test a set of CubeSat-based tribometers, and optimize the procedures so we can compare currently existing lubricants and space mechanisms. Okay, so we are planning to actually test hinges, antenna gimbals, and reaction wheels. Not the entire reaction wheel, but we will actually try to emulate maybe a bearing, that type of a small part inside the CubeSat. Okay, so what challenges I face? So in your right-hand side, you can see a kind of a standard bearing test rig. So I have the challenge of kind of miniaturizing this setup with the standards to a small 10 by 10 cube. So we have this volumetric limitation and sensor integration, because this is a kind of a satellite. So it should be an autonomous function. It should function autonomously. For now, I will not be actually launching the CubeSat to space, but I still have to test the entire CubeSat in atmospheric and vacuum conditions inside a vacuum chamber. So these are the challenges actually I'm trying to find answers. So any challenge can be answered with a good game plan. Okay, this is my game plan. So I just started my designing process. I'm still in the designing process, and I'm looking forward to optimize the design after finishing and benchmarking and comparing the existing lubricants. So this is my PhD journey. Yeah, in conclusion, there are a lot of challenges at the moment in space-based tribological tests. One main thing is cost. So we are trying to find a way across this problem by using a very economical spacecraft platform called CubeSats. And in future, of course, we will be able to actually test new lubricants, like ionic fluids, and maybe new space mechanisms, and maybe standardize these mechanisms. Okay, thank you very much for listening. If you have questions, yeah, I'm open to questions.
Thanks very much, Dan. That's very fascinating talk. Very fascinating talk on space tribology. We do have a couple of questions here in the chat. One is from Catanio Pang. The thermal variations can induce thermal material fatigue. Do thermal fatigue affect the contact surfaces and material surface microstructures? Have there been studies on lubricant degradation due to long-term exposure to thermal variations and space radiation? So kind of two questions.
Yeah, so I think I should mention first that in space tribology, we don't actually expect fatigue at all, because we cannot afford fatigue. Because if there's fatigue, it's a mechanical failure. So no, because we don't consider fatigue as a problem. Actually, design itself should actually withstand the fatigue. So main concern is lubricant degradation. Yeah, that's a very good question, valid question there. So yeah, there are a lot of studies regarding the lubricant degradation, especially in storage.
Yeah, okay. But I suppose if there are very high variations in temperature, then you are going to have a fatigue problem. I mean, it has to be solved in some way, I suppose. And maybe it's not, you're probably not studying that aspect, but it must be a big problem.
As I understand, the materials actually selected kind of in such a way that it will sustain during this ascent, the launch, and the temperature variation. So I can confirm that tribological mechanisms in space, actually, they are designed not to expect fatigue at all. Fatigue failure, actually, not the fatigue will be there, but we don't consider mechanical failure at all. So it's if there's a failure, it will be mostly lubricant failure.
Right. So I guess they're using, high fatigue resistant, high strength, high temperature resistant materials. And maybe the lubrication. So the lubrication is where the biggest problems are. Okay, there's a question from Jim Quinn. What functions does your tribometer have?
Still, I'm kind of finalizing my prototype. So I will be mainly testing a bearing test rig, not a kind of a complete rig, but it's a part of a bearing, and hinge mechanism, and most probably a gear mechanism. Still, I'm actually kind of in the process of designing these things. Yeah, I'm not sure about the exact thing I will be doing.
Okay. Question from me, maybe. I mean, so if you're trying to mimic the conditions of space, in the lab, I guess the vacuum is not terribly easy, but you can implement the vacuum. What would be the aspects that are very difficult to implement in a tribometer? The space conditions that are very difficult to implement.
Yeah, of course, that's a very good question. The main problem is we can actually emulate vacuum, maybe thermal variation, even atomic oxygen. It can be done. But the main problem is actually doing everything simultaneously at the same time, especially the radiation, space radiation. It's very difficult to actually simulate space radiation inside a laboratory condition. And doing all these kind of variables at the same time is the challenge.
Yeah, I was just wondering about how how you would simulate that radiation aspect, or even the lower gravity aspect. I mean, we're not familiar with these kind of implementing this kind of aspect, so it's very challenging, isn't it?
Yes, of course. Yeah, that's true. That's why we have to kind of work more on space-based tests.
Yeah, and would the kind of typical friction coefficients be a lot higher in space? Like I'm thinking of the kind of early experiments that Bowden and Tabor did in the 1950s, where they tested materials in a vacuum, and friction coefficients were extremely high. 5, 6, 7, 8, 9, 10, and the materials you get them really sticking together. It's a much harsher environment, I guess, and do you get much higher coefficients of friction? And
especially the metals actually in the vacuum conditions, especially stainless steel. I think in atmospheric conditions, stainless steel has a chromium oxide layer which protects the stainless steel from all the corrosion and everything. But in space, that oxide layer is going to dissolve. So the metals are completely exposed. And if there's a metal-to-metal contact, there will be a phenomena called cold welding, and it will stick together.
Wow! So you don't get the oxidation protection like you would in titanium alloys or aluminium.
No, not at all.
So you get this almost metal-to-metal contact without the oxide layer.
Yeah, in some cases, some oxide layers actually deplete slowly. But it's like zero conditions, no protection at all.
Wow, it's very interesting. There's a question here about I'm not sure what the question. It says what viscosity testing. So you might have mentioned viscosity testing. I'm not sure if you mentioned viscosity testing, but
no, I haven't mentioned anything regarding viscosity testing. Maybe it's for Emily.
It could be. There is one or two questions for Emily, actually. Emily, are you still there?
Yep, I'm still here. Yeah.
There's one from Ian Moore from JCB Hydraulics. How do you control the surface finish of the shaft and bearing?
So I've been studying the surface finish using the 3D microscope mentioned. At the minute, I'm not getting it as low as I want to go. I'm getting about 0.4 microns in the surface finish, and that's as much as I can get it to by myself. So I think I'm going to go on to potentially doing some micro polishing of the surfaces to get them down a bit more.
Okay. And there's one here. This might be for Emily. What do you mean by journal bearing loads on areas? So pressure based is the question.
So when I load the journal bearing, the loads go onto all the different pads, so you get a force on the different pads, and then like the force over area gives me the pressure on the different pads at the moment. So I'm just looking at the average pressure on each pad in the system. Yeah, I think
Okay,
just like,
so
what do you think?
so the peak pressure, I guess, could be a lot higher than the sort of average one that you calculate, but
Yeah.
you'll.
But I'm moving on to that, but all
Yeah.
I've got is average at the moment. Yeah.
Yeah, you'll be able to determine that, I guess. So not too many more questions. I think we've covered most of the questions that are here at this stage. So we're almost at 4 minutes to 1. So let me just thank the speakers again. Thanks very much to Emily Priest and to Dan for being the first speakers in the Tribology webinar series. So we hope you will also. We actually had over 50. We had about 55 attendees today. So it's that's very good amount of interest in the Tribology seminar. So hopefully you'll find some of the other talks interesting. We have one running every month. So the information is all on the IMechE Tribology group website. So it's just on the right hand side. If you go to the Tribology group website, you can see where we have the latest webinar advertised. So it's a very good window into what kind of research is going on around the UK, I think, as well, what the different groups are actually looking into. So two really excellent talks today. So I'd just like to thank Emily and Dan, and I guess we'll draw the webinar to a close. So thanks very much, everyone.